Hi there. Welcome back to our Anaqsim tutorial series. In our previous tutorial, we introduced SVAS points when creating our multi-layer model, but we didn't really dive into the details of what they are and how to use them effectively. Since SVAS points are absolutely essential for any multi-layer or transient simulations in Anaqsim, I thought it would be helpful to explain them more thoroughly. This knowledge will be incredibly useful as we move forward with more complex modeling scenarios in our upcoming tutorials. So what exactly are SVAS points? Well, SVAS stands for Spatially Variable Area Sink, and these points are where Anaqsim calculates vertical leakage between model layers and storage fluxes in transient simulations. Think of them as the calculation points that allow your groundwater to move vertically in your model. When placing SVAS points, we don't want to just guess at how to space them. Instead, we can use something called the leakage factor to guide us. So, what is the leakage factor? In simple terms, it defines the simulated horizontal distance within which we expect substantial changes in groundwater levels due to vertical flow. And since the SVAS points are where we want Anaqsim to calculate vertical flow, we need more of them in areas with stronger vertical flow. That means, when the leakage factor is small, significant vertical flow is happening over a shorter distance, so we should place our SVAS points closer together in those areas. A good rule of thumb is to space SVAS points about 1 to 1.5 times the leakage factor around discharge and recharge features, like wells, rivers, and lakes, where vertical flow is strongest. Everywhere else, where vertical flow isn't as dominant, you can space them out roughly in the same order of magnitude as the leakage factor. But remember, SVAS spacing isn't set in stone. You can adjust it any time with just a few clicks. So here's a second good rule of thumb. Start with wide spacing, at least 10 times the leakage factor, and refine it as you fine-tune your model. Anaqsim also has some great features to help you strategically target areas that need denser SVAS spacing. We'll cover those in this video. But first, let's wrap up our discussion on the leakage factor. To help grasp the concept of the leakage factor, it's helpful to look at the simplified general equation. Here it is. The leakage factor equals the square root of the transmissivity times the saturated thickness of a layer divided by the vertical hydraulic conductivity, or K3 of that layer. If we rearrange this equation a little, we can better see the effects of each parameter. Given that the transmissivity is a product of the horizontal hydraulic conductivity, K1, and the saturated thickness, B, we can rewrite the equation as the leakage factor equals the saturated thickness times the square root of K1 over K3. This version of the equation is useful because it shows that the leakage factor is directly proportional to the thickness of the model layer and depends on the ratio of horizontal to vertical conductivity. It also makes it easier to see that the leakage factor has units of length, just like we discussed earlier. That length matches whatever units you set for your model, typically meters or feet. To keep the number of SVAS points to a minimum, we can apply what we've learned from the leakage factor equation. Here's how that works in practice. Thinner model layers mean a lower leakage factor, which means we need more SVAS points. So when building your models, start with as few layers as possible. You can always add more detail later if needed. If you're simulating an isotropic system where K1 equals K3, you'll also end up with a low leakage factor, requiring more SVAS points. But in reality, most natural systems aren't isotropic. Horizontal hydraulic conductivity is usually much higher than vertical, so this usually isn't an issue. Vertical hydraulic conductivity is rarely measured directly, but a common assumption is that it's at least 1/10 of the horizontal hydraulic conductivity. The good news? You don't have to calculate the leakage factor yourself. Anaqsim does it for you and displays it in the model information display. As you move your cursor around the model, you'll see how the leakage factor changes, making it easy to spot where you need to refine your SVAS spacing. And just to reiterate, you can modify your SVAS points anytime. So there's no need to worry about having too few or too many. You can always adjust them with just a few clicks. Now let's talk about the 3 types of SVAS points in Anaqsim. Anaqsim gives us 3 different ways to add SVAS points. each with its own purpose. First, there's domain-wide SVAS. This is a basic requirement for any multi-layer or transient model. It applies SVAS points evenly across the entire model domain. In most cases, you can start with very wide spacing, unless you're working with a subdomain like a wetland or pond where vertical flow is higher. Next, we have polygon-based SVAS. This method lets you place SVAS points only in specific areas, which you define with polygons. You can even nest polygons inside each other to create different zones of refinement. This is extremely useful when you need higher density points in certain parts of your model, without increasing the total number of points everywhere else. Finally, there's well basis point SVAS. This method automatically places SVAS points around pumping wells in a radial pattern, with points getting denser as they approach the well. It's the most efficient way to capture vertical flow around a well. And here's a big plus. These points move automatically when you move your well. That means if you need to test different well locations, you won't have to manually adjust your SVAS points every time. By now, you can probably see that most models will use all three types of SVAS points at the same time. Combining them gives you the flexibility to target specific areas while keeping the overall model efficient. And when you use multiple SVAS types, Anaqsim automatically prevents points from stacking or becoming too densely spaced with a built-in overwriting system. Here's how it works. Domain-wide SVAS sets the foundation for SVAS points across the entire domain. Polygon-based SVAS overrides domain-wide. Well-basis SVAS overrides both domain-wide and polygon-based. And when it comes to nested polygons, the order of overwriting is based on a user-defined nesting level. Here's another handy feature. You only need to define your SVAS points once on any layer, and Anaqsim automatically projects them up and down to all other layers. No need to duplicate work across multiple layers. If any of this still feels a bit abstract, don't worry, we'll demonstrate everything in the next video. Now that we've covered setting up SVAS points, let's quickly look at a couple of built-in checks which help us to see if they're spaced properly. The first is a quick spot check using two key values, which you'll find in the model information display on the left-hand side of the screen. The first value, modeled extraction, is what Anaqsim calculates based on your SVAS setup. The second, extraction from heads, is what we expect based on the head differences and vertical conductivities in the model. You'll notice that these values update as you move your cursor around the domain, making it easy to make quick spot checks anywhere in your model. If they match closely, great. If not, you may need to adjust your SVAS spacing. The second check gives us the same comparison, but across an entire section of the model. Instead of just checking one point at a time, we can plot modeled extraction and extraction from heads along a transect. To do this, we need to define the section we want to analyze, and then use one of Anaqsim's analysis tools to generate the plot. For now, I just want you to know that this option exists, and in the next video, we'll walk through how to generate this plot and how to interpret it. In this video, we covered reviewing the leakage factor as a way to guide your SVAS spacing, the three different methods for adding SVAS points in Anaqsim, and briefly, we introduced two methods to check the results of your SVAS spacing. In our next tutorial, we'll put all this knowledge into practice by building a site-scale multi-layer model from scratch, incorporating everything we've learned about SVAS points. We'll see how proper SVAS placement can make a real difference in model accuracy and performance. Until next time, happy modeling.